In part 2 of section 19, we're going to look at graphs of logarithmic functions. We've already seen one graph of a logarithmic function as it relates to the inverse of the exponential function. That was done in example 19.1. In this example, we are given a function definition for f. F is given as the log base 2 of x function for f of x. Notice that the domain is not all real numbers. It is going to be from 0 to infinity. So in order to work with this, we're going to feel more comfortable looking at the logarithm in its exponential form. So I'm going to start with writing it as y equals log base 2 of x, and then I'm going to rewrite it in its equivalent logarithmic form, and or exponential form. That's going to be 2 raised to the y is equal to x. And that is not the inverse of this logarithm, that is the equivalent exponential form. So it is 100% equivalent to the logarithm. And when we go to make a table to be able to graph this function, we can pick either one of these two statements to be able to do that with. I think it's going to be easier if we do that using the exponential form. So we'll make our traditional x and y, where y is equal to, of course, f of x. But since this is set up to where the exponent is the y, and then x is going to be the answer to the exponential statement, we're not going to select x values, but instead we're going to select y values. So I'm going to select -2, -1, 0, 1, and +2. This will give us the statement x equals 2 raised to the -2. That means that 1/4 is the x value that is supposed to map to -2. Same thing is true if I look at plugging in -1. 2 to the -1st power is going to be equivalent to 1/2. So 1/2 is going to map to -1. So we're just building the table backwards because of the way that the exponential form has the y in the exponent, and then 2 to the y is what's equal to x. So if I continue to do that for the other y values, I'll have 2 to the 0 equaling 1, 2 to the 1st power equaling 2, and then 2 to the 2nd power being equal to 4. So for the graph, we're going to plot these points: 1/4 -2, 1/2 -1, 1 0, 2 1, and then 4 2. And this gives us the exact same graph that we had in example 19.1 that represented the inverse of the exponential function y equals 2 to the x. So we're going to have a vertical asymptote here located at x equals 0. And our curve is going to be increasing, going from left to right, but it's never going to get past that vertical asymptote, hence why the domain is just from 0 to infinity. So let's write down the domain for f is going to be from 0 to infinity, and the range of f is going to end up being all real numbers, which is just the exact opposite of what we had when we dealt with exponentials. The only asymptote we have here is a vertical asymptote located at x equals 0. So this is going to become our go-to picture when we start thinking about logarithmic growth. So just like with exponentials, we have the ability to talk about growth and decay, and that is entirely dependent on the value of the base. So since this base is larger than 1, we do expect there to be a growth, which would imply an increase on the graph.